Think about the most powerful ideas that have ever shaped our world, the laws that govern nations, the poems that capture the human heart, the private letters that sealed fates. For centuries, across the vast expanse of the Roman Empire, all of them started the exact same way, as dark, liquid thoughts flowing from a reed pen onto a scroll of papyrus. It's almost magical, isn't it? That something as simple as ink could be the lifeblood of an entire civilization, the physical thread connecting us to thinkers and leaders who lived 2 millennia ago. We can read their words today, but have you ever stopped to wonder about the substance that made those words permanent? What was it actually made from? This is the mystery we're setting out to solve, not in a library, but in a workshop, by stepping back in time through the raw power of experimental archaeology. Today, we are going to become Roman ink makers. We often picture history as grand statues and crumbling stone, but the real pulse of Rome was written. From the sweeping edicts of an emperor to a soldier's heartfelt letter home from a distant frontier, every mark mattered. And at the core of every one of those marks was a carefully crafted ink. This wasn't a simple substance you could just buy in a shop. It was a product of specific, almost alchemical knowledge. The ability to create a durable, rich black ink was as vital to a Roman scribe as a sharp chisel was to a sculptor. We're going to rediscover that knowledge. We will gather the very ingredients a Roman would have used. Some of them might surprise you, and we'll follow the methods described in ancient texts. This is more than a history lesson. It's a hands-on quest to see if we can truly bridge the gap between our modern world and the tangible, everyday reality of ancient Rome. So, prepare to get your hands dirty with some historical chemistry. This journey will take us from understanding why certain materials were chosen to meticulously grinding, mixing, and heating our way to a finished product. And the ultimate test, we will take the ink we create and try to write with it, just as Cicero may have drafted his speeches or as a merchant kept his accounts. It's a chance to connect, in a very direct and personal way, with the minds that built an empire. This is an invitation to join a unique experiment, to see if we can resurrect a forgotten art and, in doing so, touch the very essence of how Rome documented its glory, its dreams, and its daily life. Let's begin our journey into the fascinating world of ancient Roman ink. But before we reach for our ingredients and light our fire, it's worth pausing to ask a fundamental question. Why go to all this trouble? Why not just read about Roman ink in a book? The answer lies in the profound difference between knowing something intellectually and understanding it physically. We can read that Roman ink was carbon-based or iron-gall, but until you smell the acrid smoke from a lamp, feel the gritty texture of soot between your fingers, and witness the transformation of simple elements into a lasting liquid, the reality of this ancient technology remains just an abstract idea. This quest for authenticity is about closing that gap. It's a form of time travel achieved not with a machine, but through the meticulous reconstruction of a process. By doing what the Romans did, we gain access to a layer of historical understanding that texts alone can never provide. The muscle memory, the failed attempts, the unexpected successes, and the sheer amount of labor involved in creating something we take for granted today. Consider the sheer volume of writing that sustained the Roman Empire. Its vast administration, stretching from the rainy hills of Britain to the deserts of Syria, ran on paperwork tax records, military orders, census data. Every law passed by the Senate, every poem by Ovid, every grocery list scribbled on a wax tablet began with a scribe dipping a pen into a pot of ink. The permanence of that ink was not a trivial matter. It was a matter of state security, legal validity, and personal legacy. If an imperial decree faded to nothing within a year, the entire system of communication and control would have collapsed. By recreating their ink and testing its durability ourselves, seeing how it reacts to light, moisture, and the passage of time, we are essentially stress testing the very material that held the Roman world together. We move from seeing history as a collection of static facts to experiencing it as a dynamic system with very real physical constraints and solutions. Our guides on this journey are the Romans themselves, particularly keen observers like Pliny the Elder and the architect Vitruvius. In their encyclopedic works, they left behind recipes not as historical curiosities, but as practical instructions for their contemporaries. When Pliny describes collecting soot from specially burned resins for the best black ink, he isn't just giving us a fact. He's giving us a preference, a quality standard. By following his advice precisely, we engage in a dialogue across the centuries. Does his method truly produce a superior ink? What challenges arise that he might have considered too obvious to mention? This experimental approach allows us to interrogate the historical record in a uniquely powerful way, testing the wisdom of the ancients not with skepticism, but with hands-on curiosity. We become their apprentices, learning their craft through trial and error, and in doing so, we develop a deep, empathetic connection to the countless anonymous scribes whose hands literally wrote history. This isn't just about making ink. It's about reclaiming a lost piece of human ingenuity and appreciating the remarkable chain of innovation that allows ideas to endure long after their creators are gone. So, with our purpose clear and our historical guides chosen, our first practical step is to gather our materials, essentially recreating a Roman shopping list. This is where our experiment truly begins, moving from theory into tangible action. The most common and ancient ink, described by writers like Pliny, was a simple carbon-based ink. Its core components are just 3 items, but each one carries a story and a specific reason for its use. The first and most crucial is the pigment itself, the substance that gives the ink its color. For a deep, rich black, the Romans relied on soot, specifically a type known as lampblack. This isn't just any ash from a fire. It's the fine, powdery carbon collected from the smoke of a burning oil lamp or from burning certain resins like pine. The Romans understood that this soot was composed of incredibly fine particles that would suspend perfectly in liquid to create an opaque, lasting black. We've sourced a high-quality lampblack to mirror their process as closely as possible. Imagine a Roman scribe, perhaps late at night, carefully scraping the black residue from the inside of his clay lamp. Each batch of ink began with this patient, sooty gathering. But black powder alone is not ink, it's just dust. If you try to write with it, it would simply blow off the page. This is where the second ingredient comes in, the unsung hero of ancient inks, the binder. The Romans used gum arabic, which is the hardened sap from the acacia tree. This natural substance is a marvel of chemistry. When mixed with water, it creates a slightly sticky solution that acts as a glue, holding the soot particles together and, more importantly, fixing them permanently to the writing surface, whether it was papyrus, parchment, or even wood. The gum arabic gives the ink the right consistency to flow smoothly from a reed pen without being too watery or too thick. It transforms the soot from a loose pigment into a coherent, usable fluid. Sourcing genuine gum arabic connects us to the vast trade networks of the empire, as this material would have been imported from regions like North Africa or the Middle East. Another reminder that even a simple pot of ink was a product of an interconnected world. The third component is the simplest, water. It acts as the solvent, thinning the mixture of soot and gum to a workable consistency. Yet, even here, there might be a historical nuance. Some recipes suggest using rainwater or wine, perhaps believing they offered better properties. For our primary experiment, we'll stick with pure water to keep our variables simple. Now, while this carbon ink was the standard for centuries, the Romans were also innovators. Another type of ink began to gain prominence, one that would eventually dominate the Middle Ages: iron-gall ink. This is a more complex and fascinating chemical process. Instead of soot, its color comes from a reaction between iron salts and tannic acid, which was typically extracted from oak galls. Those strange, round growths formed on oak trees when wasps lay their eggs. When you mix a solution of iron sulfate with the tannin from crushed galls, you initially get a pale, grayish liquid, but upon exposure to air, a remarkable transformation occurs. The ink oxidizes on the page, turning a deep, enduring blue-black that is actually much more resistant to fading and washing than carbon ink. We are going to explore this variation as well, because it represents the cutting edge of Roman ink technology. Gathering the ingredients for iron-gall ink is a different kind of hunt. It means finding oak galls, which are like little wooden apples, and obtaining iron sulfate, a green crystalline salt that Romans might have collected from mine runoff or produced through basic chemistry. By attempting both recipes, we get a fuller picture of the Roman scribe's toolkit. He might have used the reliable, instantly black carbon ink for everyday documents, but for something meant to last forever, a legal contract or an important manuscript, the permanent chemical bond of iron-gall ink would have been the superior choice. Assembling these ingredients is more than just preparation. It's the first lesson in the material reality of the ancient world, appreciating why each component was selected not by chance, but through centuries of experimentation and refined craft. With our ingredients waiting on the workbench, our attention turns to the instruments that will bring them together. The process of transforming raw soot and gum arabic into a smooth, flowing ink is as much about the tools as it is about the recipe. A Roman scribe setting up his workspace wouldn't have reached for a digital scale or a stainless steel whisk. His toolkit was one of elegant simplicity, drawn from the materials readily available in his world. The centerpiece of his operation would almost certainly have been a mortar and pestle. This wasn't just for crushing spices. It was the essential first step for grinding the lumpy gum arabic into a fine powder and then meticulously incorporating the soot to create a perfectly homogeneous pigment. We've chosen to use a heavy stone replica mortar and pestle to immerse ourselves fully in the tactile reality of this ancient task. The weight of the stone, the gritty sound of the grinding, and the sheer physical effort required provide an immediate and powerful connection to the countless individuals who perform this very action for their livelihood. Yet, to truly understand the Roman method from a modern scientific perspective, we also need precision. This is where our experiment takes a dual approach. Alongside our replica mortar and pestle, we have modern measuring spoons and a digital scale. Why this split personality? It allows us to appreciate the Roman experience while simultaneously ensuring our results are accurate and repeatable. When the ancient texts say to use a portion of gum or a handful of soot, those are wonderfully vague instructions that leave a lot to interpretation. By carefully measuring our ingredients in grams and milliliters after we've worked with them using the ancient tools, we can record an exact formula. This means that if we succeed in creating a fantastic ink, anyone else can replicate our results precisely. It's a bridge between the subjective, experience-based knowledge of the ancient world and the objective, data-driven approach of our own. We can feel what a sufficient grind feels like in the mortar, and then we can quantify exactly what that amounts to. The container for mixing the ink is another point of fascinating comparison. A Roman would have likely used a small ceramic cup or a glass bowl. We have a simple terracotta vessel, not unlike one that might have been dug up from a Roman site. There's a certain authenticity to watching the ink components swirl together in a pot that looks and feels genuinely ancient. However, we also have a clear glass beaker standing by. The beaker offers a practical advantage, complete visibility. We can watch the ink's consistency develop, see how the powder incorporates with the water, and spot any potential clumps instantly. This visual feedback is invaluable for learning the nuances of the process, something the Roman ink maker would have had to judge purely by feel and by the look of the ink on his finger or a test scrap of material. Finally, consider the application of heat. Some recipes suggest gently warming the mixture to help the gum arabic dissolve more completely. A Roman might have set his ceramic vessel near the embers of a cooking fire or on a small brazier, carefully regulating the temperature by instinct and experience. For our controlled experiment, we'll use a modern hot plate. This gives us a consistent, adjustable heat source that eliminates one major variable, the risk of burning the ink or overheating the mixture. By comparing the two approaches, we gain a deep appreciation for the skill involved in managing such a delicate process with primitive technology. The Roman scribe wasn't just a writer, he was a craftsperson, a chemist, and a master of his tools. Our side-by-side setup, ancient and modern, allows us to deconstruct that craftsmanship, to understand not just what they did, but how they did it, and to measure the gulf between their intuitive art and our precise science. This comparison sets the stage for the most hands-on part of our journey, the actual creation of the ink. So we have our ingredients laid out and our tools ready, but how do we know what to do with them? We aren't guessing, we are following a trail of clues left behind in ancient texts. Our primary guide is the Roman encyclopedist Pliny the Elder, whose massive work, The Natural History, attempts to document everything known about the world in the 1st century. Buried within its volumes is a brief but crucial mention of ink. He writes about the best black pigment coming from the soot of burned resins, specifically pine wood, collected in a specially constructed furnace. This is our starting point, a direct observation from a Roman who would have seen this process in action. But Pliny wasn't writing a detailed manual for future archaeologists. His description is concise, almost incidental, as if he's reminding his readers of something they might already know. He doesn't give us precise ratios or step-by-step instructions. He gives us a key ingredient and a hint about its quality, leaving us to fill in the considerable gaps with practical experimentation. This is where the work of modern historians, philologists, and chemists becomes absolutely essential. Translating a word like atramentum from Pliny's Latin is the first challenge. This term can mean any black dye or pigment, from writing ink to shoe polish. The context is what narrows it down to ink for writing. Then comes the interpretation of his technical descriptions. When Pliny talks about constructing a furnace to collect the soot efficiently, he assumes his reader understands the architecture of a 1st century industrial setup. We don't. So, scholars have had to cross-reference his words with archaeological finds, remains of ancient workshops, residue analysis on ink pots, to reconstruct what that furnace might have looked like. It's a collaborative puzzle, piecing together literary fragments with physical evidence. For the more complex iron-gall ink, we look to slightly later sources, though ones that undoubtedly have Roman roots. The detailed recipes appear most prominently in medieval manuscripts, but the technology was clearly in use during the later Roman Empire. These medieval recipes are often more explicit, sometimes written by monks in scriptoria who depended on reliable ink for their daily work. A typical recipe might instruct you to take a certain measure of crushed oak galls, soak them in rainwater, then add iron sulfate, and finally thicken it with gum arabic. Yet, even these more detailed instructions are fraught with ambiguity. What size are the oak galls? How long is soak for several days? What is the exact purity of the iron sulfate? The medieval scribe, like his Roman predecessor, was working with materials of variable quality, relying on his experience to adjust the formula until it looked right. This vagueness is not a flaw in the historical record. It's a feature of pre-industrial craftsmanship. Knowledge was often transmitted orally and refined through hands-on practice. A master would teach an apprentice the general principles, and the apprentice would learn the nuances through years of repetition. The written recipe was a memory aid, not a complete specification. For our modern experiment, this means we cannot simply follow a single ancient text and expect perfect results. Instead, we have to become like those apprentices, consulting multiple sources, Pliny, Vitruvius on pigments, later medieval manuscripts, and then making informed decisions. We combine the historical hints with basic chemistry. We know, for instance, that the key reaction in iron-gall ink involves tannic acid bonding with iron ions to form a black compound. This scientific understanding allows us to interpret a vague instruction like add until it turns black with more precision. We can test the pH, we can calculate approximate ratios, and we can create a formula that is historically plausible while being scientifically sound. This fusion of old words and new knowledge is the heart of experimental archaeology, turning cryptic descriptions into a tangible, testable process. Now, the theoretical groundwork is laid, and it's finally time to get our hands truly dirty with the first tangible act of creation, preparing our core pigment. We have our small jar of lampblack, a fine, fluffy powder that feels almost weightless. But this isn't the end of the journey for the soot. In fact, this is where the real transformation begins. The initial consistency of the lampblack, as collected, can be surprisingly clumpy. If we were to simply mix it with water and gum, we'd end up with a gritty, uneven slurry that would be a nightmare for any scribe. So our first task is to take this raw material and refine it into the finest powder possible using the most fundamental tool in the ancient workshop, the mortar and pestle. The act of grinding is deceptively simple. You pour a small amount of the lampblack into the stone mortar, and then you begin the rhythmic, circular motion with the pestle. At first, it feels like you're just pushing around a soft black cloud, but after a minute or two, you start to feel a change. The texture under the pestle becomes smoother, more silky. You can actually hear the difference. The initial soft crush of tiny aggregates gives way to an almost silent, fluid movement. This is the sound of success, the sound of individual carbon particles being separated and reduced to a state of ultimate fineness. A Roman ink maker would have judged this entirely by feel, and by carefully examining a small pinch of the powder rubbed between his fingers. He was looking for a complete absence of grittiness, a texture as smooth as the finest flour. This tactile quality check was his only assurance of a quality product. Why is this step so critical? It all comes down to the physics of writing. The ancient reed pen, with its finely cut nib, has a delicate channel to draw up the ink. If the pigment particles are too large or coarse, they act like tiny grains of sand, quickly clogging the nib and causing the ink flow to sputter and stop. Every time the scribe would have to stop and clean his pen, his train of thought would be broken, and the rhythm of his work would be lost. On the other hand, if the particles are ground to an exceptionally fine and uniform powder, they suspend perfectly in the liquid binder. This creates a homogeneous ink that flows smoothly and consistently from the pen, leaving a clean, sharp line on the papyrus. The difference between a clogged pen and a smooth one is literally in the grind. It's a perfect example of how a seemingly minor preparatory step had a direct and profound impact on the efficiency and quality of the final act of writing. Beyond mere functionality, the fineness of the grind also affected the ink's aesthetic quality and durability. A poorly ground ink would produce a pale, blotchy line because the larger particles would not distribute evenly. The writing would look weak and unprofessional. A properly prepared ink, however, would lay down a dense, opaque, and deeply black line that was not only beautiful but also more permanent. The fine particles, locked in place by the gum arabic, would have a much greater surface area to adhere to the papyrus fibers, creating a stronger bond that was less likely to flake off over time. This meticulous preparation, therefore, wasn't just about making the ink easier to use. It was about ensuring the words it formed would endure. It's a powerful reminder that the permanence of Roman records wasn't an accident. It was the direct result of a carefully mastered craft, starting with the patient, deliberate turning of a stone pestle in a mortar. With our lamp-black ground to a state of velvety perfection, we turn our attention to what might seem like a simpler task, but one that is equally vital, creating the liquid glue that will hold our pigment together. This is the job of the binder, and for our Roman-style ink, that means working with gum arabic. These are not smooth pellets or a ready-made liquid. What we have are rough, translucent crystals, almost like tiny shards of amber. Their appearance is deceptively simple, because transforming them into the perfect binder is a process that can't be rushed. We carefully measure a portion of these crystals into our terracotta bowl, and then we add warm water not boiling, but pleasantly hot. The initial reaction seems almost inert. The crystals just sit there, cloudy and separate. This is where patience becomes our most important tool. Over the next several minutes, with occasional gentle stirring, we witness a quiet miracle of chemistry. The crystals begin to absorb the water, swelling and softening, slowly releasing their complex sugars into the solution. What was once clear water becomes increasingly cloudy and syrupy. The goal is to achieve a solution with the consistency of thin honey, a liquid that is noticeably viscous, that coats the spoon and drips slowly. This transformation is crucial because the gum arabic solution serves two absolutely essential functions. First, and most obviously, it is the adhesive. If you were to simply mix our beautifully ground lampblack with plain water and try to write with it, you'd be in for a disappointment. As soon as the water evaporated, the black pigment would have nothing holding it to the page. The slightest touch, a breath of air, would cause the soot to dust away completely, leaving behind a blank surface. The gum arabic molecules form a sticky matrix that encases each individual particle of carbon and, upon drying, creates a strong, flexible film that locks the pigment permanently onto the papyrus or parchment fibers. It's the difference between throwing sand at a wall and gluing it there. One is temporary, the other is made to last. But the second, more subtle function of the gum arabic is just as important. It controls the ink's body and flow. The viscosity of the solution determines how the ink behaves when it meets a reed pen. If the mixture is too thin and watery, it will flood out of the pen's nib, creating blots and bleeding uncontrollably into the writing material. It would be like trying to write with black-colored water. If, on the other hand, the mixture is too thick and gloopy, it won't flow at all. It would clog the narrow channel of the pen instantly, forcing the scribe to stop and clean the nib after every letter. The ideal gum arabic solution achieves a perfect balance. It is thin enough to be drawn up by the pen's capillary action, yet thick enough to cling to the nib and be released in a controlled, steady line as the pen moves across the surface. This precise consistency allows for the graceful, connected strokes of cursive handwriting or the deliberate, formal characters of a manuscript. The gum arabic doesn't just make the ink stick, it makes the ink write. As we continue to stir, watching the solution gradually thicken, we're not just making glue. We are fine-tuning the very character of our ink, preparing it for its ultimate purpose of carrying thought into permanent form. Now we arrive at the heart of the entire endeavor, the moment where our separate preparations become one. With our soot ground to a velvet fineness and our gum arabic solution achieving that perfect, honey-like consistency, it's time for the grand mixing. This is far more than just stirring two things together. It's a delicate act of fusion where patience is the most crucial ingredient. We take a small pinch of our lampblack, and with the care of a chef adding a precious spice, we begin to sprinkle it onto the surface of the clear, viscous gum solution. The initial contact is dramatic. Each dark particle hits the liquid and immediately blossoms into a tiny, swirling black cloud, like a drop of ink in water, but in reverse. We must add the pigment incredibly slowly, allowing each addition to be fully incorporated before introducing more. The tool for this is a simple wooden spatula, and the motion is everything. We don't stir aggressively, which would trap air bubbles and create a foamy mess. Instead, we use a gentle, folding motion, pressing the soot down into the liquid and drawing the clear gum up from the bottom over and over again. It's a rhythmic, almost meditative process. At first, the mixture looks streaky and incomplete swirls of deep black marbling through the golden brown gum arabic. But with each passing minute and each careful fold, the two substances begin to lose their individual identities. The color deepens from a murky brown to a definite gray, and then, as we continue to add more soot and blend, it finally achieves that profound, light-absorbing black we've been seeking. Watching this transformation is truly alchemical. You are witnessing the birth of ink before your eyes. This is where the Roman craftsman's skill truly shone. He didn't have a written recipe with exact measurements. He had a feel for the correct consistency. As we stir, we constantly assess the ink's body. We dip the spatula out and let a drop fall back into the bowl. How does it drip? Is it too watery, spreading out quickly? Then we need to add more of our precious ground, soot, to increase the opacity and thickness. Is it too pasty, clinging stubbornly to the wood? Then we incorporate a few more drops of warm water to improve its flow. This tactile feedback loop is the essence of ancient craftsmanship. The goal is a perfect balance. An ink that is dark enough to be perfectly readable, but fluid enough to glide from a pen without hesitation. It should coat the spatula evenly, leaving a glossy, unbroken film, not a lumpy or translucent one. Achieving this is a triumph, a direct result of the careful preparation of both our pigment and our binder. The final mixture should have the smooth, rich appearance of fresh espresso, a liquid that promises permanence with every drop. The true test of our ink lies not in its color but in its behavior. We've created a substance that looks the part, with a deep, glossy blackness, but the final and most critical judgment comes from its viscosity. Is it too thick, refusing to flow from a pen? Or is it too thin, spreading like a stain on the page? To answer this, we move from the mixing bowl to the testing phase, using a method any Roman scribe would recognize instantly. We take a freshly cut reed pen, its nib carefully split to form a channel, and dip it into our mixture. The first sign of success is a subtle one. The ink should be drawn up into the shaft of the pen through capillary action, that same physical principle that draws water up a plant's roots. If the ink is too viscous, it will stubbornly cling to the outside of the nib, failing to be pulled inside. If it's too watery, it will flood the channel immediately, overwhelming it. We lift the pen and hold it poised over a scrap of papyrus. This is the moment of truth. We watch how the ink drips, or rather, how it doesn't. A single, well-formed droplet should gather at the tip, holding its shape for a few seconds before finally falling. This indicates a perfect balance, enough body to cling together, but enough fluidity to release when needed. If multiple drops fall in rapid succession, the ink is too thin. If no drop forms at all, it's too thick. Next, we touch the nib to the writing surface. The ink should transfer smoothly, forming a clean, sharp line without any blobbing or skips. As we write a few characters, we're looking for a consistent flow that keeps up with the speed of our hand. If the line is faint or broken, the ink needs more pigment. If it feathers outwards, bleeding into the papyrus fibers in a fuzzy halo, the mixture lacks body and requires more gum arabic to hold its shape. To give you a more familiar reference, we can compare our homemade ink to a modern calligraphy ink. A commercial ink is engineered for perfect consistency every time. It's a known quantity. Our Roman ink, by contrast, is a living substance we've coaxed into existence. It might have a slightly different feel, perhaps a bit more organic, a little less predictable. This isn't a flaw, it's a characteristic of a handcrafted product. The Roman scribe would have known his particular batch intimately, understanding its quirks and adjusting his writing pressure and speed accordingly. This testing process is where theory meets practice, where our carefully measured ingredients and patient grinding are validated by the simple, elegant act of putting pen to paper. It's a direct dialogue with the past, using the same fundamental criteria to judge a product's quality. Our freshly mixed ink may look perfect in the bowl, but its true character is only revealed when it meets a writing surface. To understand the choices a Roman scribe made every single day, we need to see how our creation performs on the two most important canvases of the ancient world, papyrus and parchment. The difference between them is not just about material, it's about purpose, cost, and the very personality of the written word. We have small pieces of both, made using historical methods, and watching the ink interact with each one tells a story centuries old. First, we try the papyrus. This is the iconic writing material of antiquity, made from the pith of the papyrus plant, sliced thin, layered crosswise, and pressed together. Its surface is surprisingly smooth, but has a distinct texture, like a very fine woven fabric. When we dip our reed pen and draw the first stroke, the result is immediate and fascinating. The ink seems to sink into the papyrus almost the instant it touches the surface. It doesn't spread outwards in a feathery pattern. Instead, it is pulled directly down into the plant's fibrous network. This creates a very sharp, crisp edge to the letters. The line is bold and dark, but it has a slightly matte, absorbed quality. there's very little sheen. This absorption is a double-edged sword. On one hand, it means the writing dries quickly and is resistant to smudging once set. On the other hand, it leaves little room for error. If a scribe hesitated or made a mistake, the ink would already be locking into the fibers, making correction very difficult. This characteristic explains why papyrus was so favored for administrative documents, letters, and drafts. It was practical, relatively quick to produce, and ideal for the fast-paced, utilitarian writing that kept the empire's bureaucracy humming. Then we turn to the parchment. This is an entirely different beast, made from animal skin that has been scraped, dried, and stretched under tension. Its surface is incredibly smooth and almost plastic-like. The moment our pen touches it, the ink behaves completely differently. Instead of soaking in, it seems to sit on top of the surface, pooling slightly before slowly drying. The line it produces is glossier and has a deeper, more pronounced black because the ink isn't being absorbed and diluted by the material underneath. This allows for incredible precision and very fine hairlines, making it the superior choice for deluxe manuscripts, important legal contracts, and any work where presentation and longevity were paramount. However, this non-absorbent quality has its own challenges. The ink takes much longer to dry, leaving it vulnerable to smudging from a careless hand. It also requires a more controlled hand from the scribe. If you apply too much pressure or hold the pen in one spot, the ink can blob and create an unsightly spot. The choice between papyrus and parchment, therefore, wasn't just about what was available. It was a deliberate decision based on the document's purpose. A tax collector in Egypt would reach for a sheet of papyrus for his records, while a scribe in Rome commissioned to copy Virgil's Aeneid for a wealthy patron would undoubtedly choose the superior, more expensive surface of parchment to do the poetry justice. While our rich carbon ink represents the classic standard of antiquity, the Romans were not content to stand still. Their drive for improvement led to the development of another, far more chemically sophisticated ink, iron-gall ink. This isn't just a different recipe, it's a completely different principle. Instead of relying on a physical pigment like soot suspended in a binder, iron-gall ink creates its color through a fascinating chemical reaction that literally unfolds before your eyes. To understand this process is to appreciate a significant leap in ancient technology, one that would dominate writing for over 1,000 years. Our next task is to gather the strange ingredients for this alchemical transformation, starting with the most peculiar one, oak galls. If you've ever walked through an oak forest and noticed hard, spherical growths clinging to the branches, looking like little wooden apples, you've seen galls. These are not a natural part of the tree. They are its defensive response to an intruder. A tiny gall wasp lays its egg in the bark, and the tree, in an attempt to isolate the irritant, grows a protective shell of dense, tannin-rich tissue around it. For the ink maker, this shell is the treasure. The tannic acid concentrated within these galls is incredibly potent. When we crush them, a task that requires a good deal of force with a mortar and pestle, we release this tannin. The crushed galls are then soaked in warm water for a day or more, creating a dark, astringent brown liquid that smells faintly of tea. This tannin solution is one half of our reactive pair. The other half is the source of the iron in iron-gall ink, iron sulfate, a compound historically known as green vitriol. This material would have been familiar to the Romans, who might have encountered it as a crystalline residue forming in mines where iron ore was exposed to air and water, or as an industrial byproduct. It appears as pale green, translucent crystals. On its own, it seems entirely unremarkable, but when we dissolve these crystals in water and then carefully mix this solution with our tannin extract, something magical happens. At first, the mixture is a pale, murky gray, almost disappointingly faint. There is no immediate deep black, but then, as we expose it to the air, a slow transformation begins. The ink darkens on the page over several minutes, eventually settling into a deep, blue-black hue that is far more permanent than any carbon ink could ever be. The science behind this is remarkable. The tannic acid from the galls reacts with the iron ions from the sulfate salt. In the liquid mixture, this reaction is limited. But the moment the ink is applied to a writing surface and exposed to oxygen in the air, a process called oxidation takes over. The iron tannate complex that forms is not just a surface stain. It actually bonds chemically with the cellulose in papyrus or parchment, becoming an integral part of the material itself. This is why iron-gall ink is so famously resistant to fading, water, and even scraping. It doesn't just sit on top of the page, it becomes one with it. This chemical permanence made it the preferred choice for the most important documents, legal charters, royal decrees, and religious texts where the longevity of the words was paramount. By embarking on this second recipe, we are not just making another kind of ink. We are replicating a technological breakthrough that ensured the survival of Western history itself. Now, for the moment that truly feels like ancient alchemy, we combine our two prepared solutions, the dark, tea-like tannin extract from the oak galls and the pale green liquid of dissolved iron sulfate. The initial mixture is startlingly unimpressive. Instead of the deep black we expect, we get a murky, watery gray, the color of a stormy sea. It's so faint you might worry the entire process has failed. But this is where the real magic begins. We take a reed pen, dip it into this seemingly weak concoction, and draw a line across a piece of parchment. The mark it leaves is barely visible, a soft, shadowy gray. Then we wait. Over the next 30 to 60 seconds, a silent, invisible transformation takes place. It's as if the line is drawing a breath, gathering its strength. Gradually, right before our eyes, the pale gray begins to deepen. It shifts to a dusky purple, then a blue-gray, and finally settles into that iconic, profound blue-black that has characterized important documents for over a millennium. The change is not instantaneous. It's a slow, deliberate unveiling of permanence. The science behind this beautiful transformation is a brilliant piece of chemistry that the Romans harnessed, even if they didn't fully understand the molecular details. The key player here is oxygen from the air. In the liquid state, the iron ions from the sulfate and the tannic acid from the galls have combined to form a complex, but it's in a reduced, colorless or pale form. The moment this mixture is applied to a surface and exposed to the atmosphere, oxygen molecules rush in. They oxidize the iron in this complex, changing its chemical state. This newly oxidized iron tannate compound is intensely dark and, most importantly, completely insoluble in water. But the magic goes even deeper. This new compound doesn't just sit on top of the parchment or papyrus like a layer of paint. It actually forms a strong chemical bond with the cellulose fibers of the writing material itself. The ink becomes a part of the page, creating a mark that is incredibly resistant to fading from light and nearly impossible to wash away with water. This is a fundamental difference from carbon ink, which is essentially a physical layer of soot glued on the surface. Iron-gall ink is a chemical integration, a fusion of ink and page. This superior durability is precisely why iron-gall ink became the undisputed champion for recording anything that needed to last forever. While carbon ink was perfect for everyday notes, letters, and administrative scrolls, the most vital records of the empire and later the medieval world were written with iron-gall. Think of the Magna Carta, Da Vinci's notebooks, or Bach's musical scores. Their survival owes a great debt to this chemical innovation. A document written in carbon ink could be smudged or washed away by a spill. Exposure to light would slowly cause it to fade. But a contract written in iron-gall ink was for the ages. Its resistance to forgery was also a key advantage. Attempting to scrape away the writing would damage the actual fibers of the parchment because the ink was bonded to them, leaving clear evidence of tampering. This combination of self-revealing permanence and defensive security made it the ultimate choice for laws, treaties, land deeds, and sacred texts. By successfully recreating this reaction, we aren't just making a different color of ink. We are witnessing the very chemical principle that secured the written legacy of the Western world. Standing here with two small pots of ink, one a deep velvety black and the other a cool blue-black, is like holding two different philosophies of permanence from the ancient world. The simple soot-based ink, made from lampblack and gum arabic, is the classic workhorse. Its greatest advantage is its immediacy. From the moment you mix it, it's ready to write, producing a rich, opaque black line right from the first stroke. For a Roman accountant tallying up grain shipments in a busy port, or a military clerk recording supplies for a legion on the move, this speed and reliability would have been essential. There's no waiting, no complex chemistry to manage. It's the ink of daily life, of commerce and quick communication. However, this convenience comes with a significant trade-off. Carbon ink is fundamentally a physical layer. The gum arabic acts as a glue, sticking the soot particles to the surface of the papyrus or parchment. While effective, this bond is vulnerable. A spilled cup of water could wash the words away into a murky puddle. Prolonged exposure to sunlight would slowly, but surely, cause the black to fade to a faint brown as the carbon particles were gradually bleached away. A document written in carbon ink required careful handling and storage if it was meant to last more than a few years. The iron-gall ink, on the other hand, is the patient strategist. It doesn't reveal its full strength immediately. As we saw, it starts pale and gains its darkness through a slow, deliberate reaction with the air. This ink wasn't for the hurried note-taker. It was for the scribe tasked with creating something for the ages. Its permanence is not just superior, it's of a different kind altogether. Because it chemically bonds with the cellulose in the writing material, it becomes part of the page itself. You could spill water on a contract written in iron-gall ink, and while the parchment might warp, the words would remain perfectly legible. This incredible durability also made it a powerful tool against forgery. Attempting to scrape away iron-gall writing would damage the actual fibers of the parchment, leaving obvious evidence of tampering. For recording laws, treaties, land deeds, or sacred texts, this combination of resilience and security was unmatched. The complexity of its production was a price worth paying for the assurance that the words would endure. So, who would have chosen which? Imagine a poet in a sunlit villa, drafting verses. He might reach for the carbon ink. Its immediate, rich blackness would flow smoothly from his reed pen, allowing him to capture the spontaneous rush of inspiration without interruption. The poem itself, once perfected, might then be copied onto finer parchment using iron-gall ink by a professional scribe for presentation to a patron. The poet values the tool that keeps pace with his thoughts. while the patron values the permanent artifact. Conversely, an imperial archivist in Rome, responsible for preserving the official copies of Senate decrees, would never consider anything but iron-gall ink. For him, the entire purpose of his work was to create a record that would outlast the marble of the buildings themselves. The choice between these inks was never just about black versus blue-black. It was a decision based on the intended lifespan of the message and the very nature of the words being written. Our journey into the heart of Roman writing now brings us to a tool that is deceptively simple yet demands immense skill to master: the calamus, or reed pen. We have our ink meticulously crafted and waiting in its pot, but without the proper instrument to deliver it to the page, it is just a dark liquid. The transition from a modern ballpoint pen to a hand-cut reed is one of the most humbling experiences in this entire experiment. It instantly redefines your understanding of what it meant to write in the ancient world. This isn't about putting words on a page. It's about conducting a delicate negotiation between a flexible nib, a watery ink, and an absorbent surface. The first challenge is creating the pen itself. We start with a dry section of a common reed, a material that grows abundantly along riverbanks. It feels light and almost fragile in the hand, but its fibrous structure gives it a surprising strength. The first cut is the most critical, a sharp, diagonal slice across the tip to create the fundamental writing point. But that alone is not enough. To truly function, the reed needs a reservoir to hold the ink and a channel to guide its flow. This is where the real craftsmanship begins. Using a very fine knife, we make a second, careful cut to split the very tip of the diagonal point, creating a tiny fork. This split is the heart of the calamus. It acts as a capillary channel, drawing the ink up from the dip and holding it ready for writing. The final step is to gently sharpen the two resulting tines to a fine point, being incredibly careful not to split the reed further up the shaft. A pen that is cut too deeply will simply dump all of its ink in a single blot. A pen cut too shallowly will refuse to write at all. Achieving that perfect balance is a skill that a Roman scribe would have practiced until it became second nature. Now comes the true test: actually writing. Dipping the reed into the ink pot feels familiar, but the moment you lift it and bring it toward the papyrus, everything changes. A modern pen relies on gravity and a rolling ball to dispense ink consistently. The reed pen operates on an entirely different principle: capillary action. The ink is drawn up into the narrow split of the nib and is held there by the liquid's own surface tension. This means the ink flow is not automatic. It is entirely dependent on the angle and pressure you apply. Hold the pen too upright, and the angle breaks the capillary pull, stopping the flow completely. Hold it too flat, and the entire slit makes contact with the page, releasing a flood of ink that creates an instant blot. The ideal angle is a surprisingly shallow one, around 45 degrees, allowing just the very tip of the nib to glide across the fibrous surface. Then there is the pressure. Press too hard, and you force out more ink than the capillary action can replenish, leading to a faded, skipping line as the pen runs dry mid-stroke. Press too lightly, and the nib barely touches the page, producing a faint, broken ghost of a line. The sweet spot is a gentle, consistent drag, a feather-light touch that maintains constant contact. Your entire hand, wrist, and arm must learn a new kind of discipline, a controlled grace that feels completely foreign to anyone used to the forgiving pressure of a ballpoint. This physical relationship between the tool and the writer had a profound influence on the very style of Roman script. The classic Roman capital letters, with their elegant serifs and strong vertical strokes, are a direct result of the reed pen's capabilities and limitations. The thick downstrokes come naturally from a slight hesitation or increase in pressure as you pull the pen toward your body. The thin, delicate horizontal strokes are achieved by pushing the pen sideways with a lighter touch, a motion that inherently releases less ink. Those distinctive serifs, the small feet at the end of the letter strokes, are not merely decorative flourishes. They are the natural starting and stopping points of the pen. To begin a letter, a scribe would place the pen down and make a small, preparatory stroke to get the ink flowing before pulling the main line. To finish, he would lift the pen with a slight flick, leaving a tiny terminal mark. What we see as beautiful calligraphy was, in many ways, the most efficient and reliable way to use this particular tool. It was an ergonomic adaptation, a style born from the material reality of the reed and the ink. Trying to write quickly with this instrument is nearly impossible. It forces a deliberate, thoughtful pace. Every word must be formed with intention. This slow, measured process makes you appreciate the incredible speed and consistency of professional Roman scribes, whose hands had been trained to make this difficult tool an extension of their own thought, turning the slow trickle of ink into a river of recorded language. But we've created more than just ink. We've created a question. How do we know if the words we write today with this historically accurate recipe would actually survive for centuries, like the documents that inspired this entire project? We can't simply put our samples in a drawer and check back in the year 424. Instead, we turn to a fascinating field of scientific analysis known as accelerated aging. This is our time machine, a way to simulate the slow, relentless effects of centuries in a matter of days or weeks. The principle is straightforward but powerful. By intensifying the very forces that degrade organic materials, light, heat, and moisture, we can observe and fast forward how our ink will behave over the long term. Our first and most formidable adversary is light, specifically the ultraviolet component of sunlight. This invisible energy is incredibly destructive at a molecular level, breaking down the chemical bonds that give pigments their color and binders their strength. To test this, we've prepared identical samples on both papyrus and parchment, writing the same characters with our carbon ink, our iron-gall ink, and, for a crucial point of comparison, a standard modern calligraphy ink. We'll place these samples under a specialized UV lamp, which emits a controlled intensity of ultraviolet light far greater than normal indoor lighting. Over the course of several days, this lamp will deliver a dose of UV equivalent to what a document might receive if it were stored in a shaded but not dark room for many decades. We will periodically examine the samples, looking for the telltale signs of fading. Will our carbon ink, a physical layer of soot, begin to turn a rusty brown as the carbon particles are gradually bleached? Will the modern ink, with its complex synthetic dyes, fade uniformly or change color in an unexpected way? And most importantly, will our iron-gall ink, with its deep chemical bond to the page, prove its legendary resistance? The second test involves heat and humidity, the silent partners in decay. High temperatures accelerate chemical reactions. For every 10 degrees Celsius you increase the temperature, the rate of many degradation processes can double. We will place another set of our written samples in a controlled environment chamber, sometimes called a humidity oven. Here, we can subject them to elevated temperatures and controlled moisture levels that mimic the conditions inside an attic, in a warm climate, or a stone building that experiences seasonal dampness. This test is particularly brutal for the carbon ink and its gum Arabic binder. The heat can make the gum brittle, causing it to crack and lose its adhesive power, while high humidity can encourage microbial growth that actually consumes the organic binder. We'll be watching carefully to see if the carbon ink begins to flake away from the page when gently brushed. The iron-gall ink faces a different challenge. In very high humidity, the iron compounds can sometimes continue to react, potentially leading to a phenomenon known as ink corrosion, where the acidic ink actually eats through the parchment over centuries. Our accelerated test might reveal the earliest signs of this, a slight browning or weakening of the parchment directly under the written lines. After running these tests, the moment of truth arrives. We take our aged samples and compare them side by side with control samples that have been kept in a dark, stable environment. The differences can be startling. The modern ink might have faded to a pleasant but pale version of its original self, proving comfortable for short-term use, but vulnerable over the long haul. The carbon ink may show significant fading, and perhaps even some powdering, especially on the edges of the strokes where the binder was most exposed. The real champion, we expect, will be the iron-gall ink. Even under the harsh UV light, its blue-black hue should have darkened slightly but remained intensely legible. The heat and humidity test might show no flaking at all, because the ink isn't sitting on the surface. It has become one with the material. This hands-on validation is the ultimate goal of our experimental archaeology. It moves us from reading about the durability of Roman ink in a book to witnessing it with our own eyes, providing tangible, physical evidence for why certain technologies were adopted and cherished. It's a powerful testament to the ingenuity of ancient craft, proving that their solutions weren't just effective for their time, but were engineered with a foresight that we can still measure and admire today. Now that we have our inks and we've seen how they write, let's look much, much closer. To the naked eye, both of our creations appear as a deep, solid black. But if we could see them through the eyes of a master Roman scribe, a man whose entire livelihood depended on the quality of his materials, we would notice a world of difference. The true character of an ink is often revealed not in its initial impression, but in its subtle undertones. To explore this, we're going to place drops of our inks on a white tile and examine them under strong magnification, observing how they behave as they dry and what hidden colors they reveal. This is where we move beyond simple functionality and into the realm of aesthetic nuance, a nuance that a discerning ancient eye would have been highly attuned to. Our carbon ink, made from the lamp black, is the first under the lens. While it appears jet black in the pot, the magnified view tells a more complex story. As it dries on the pure white surface, a slight warmth emerges around the edges. This isn't a defect, it's a direct result of the carbon source. Soot is not a single, pure chemical. It's a complex mixture of carbon compounds, and its exact color can be influenced by what was burned to create it, and how completely it was burned. Soot from a pine resin, which Pliny the Elder praised, might have a slightly different hue than soot from an olive oil lamp. Under magnification, our lamp black ink shows a very subtle, almost rusty brown undertone. This gives the black a certain warmth, a richness that is actually quite beautiful and would have been perfectly suitable for the vast majority of documents. A scribe might have even preferred this slightly warmer black for everyday writing, as it could be easier on the eyes under the bright Mediterranean sun than a stark, cold black. Then we turn to the iron-gall ink. Its transformation is complete. It has oxidized to its final state. Under magnification, the difference is striking. This ink lacks the warm, earthy undertones of the carbon ink. Instead, it presents a much cooler, more neutral black. In certain lights, especially when a thin layer is smeared, it can even have a faint blue-gray or violet cast to it. This is the signature of a pure iron tannate complex. It's a colder, more severe black, the color of a moonless night or deep water. For a scribe working on an important, permanent document like a legal charter or a deluxe manuscript, this cool, unwavering black would have been the mark of highest quality. It signified permanence and chemical purity. There would be no risk of the document developing a brownish tint over time, as can happen with some carbon inks. The iron-gall ink was designed to darken and stabilize with age, becoming even more fixed to the page. This attention to subtle color variations speaks to a refined artistic sensibility in the Roman world. We often think of them in terms of engineering and conquest, but their appreciation for craft extended to these minute details. A scribe wouldn't just want an ink that worked. He would want an ink that looked right for the task at hand. The warm black of the carbon ink might be seen as more approachable, more human, perfect for a personal letter or a poet's draft. The austere, cool black of the iron-gall ink conveyed authority, finality, and a commitment to the ages, making it the only choice for an imperial edict. This level of discernment transforms the scribe from a simple copyist into a true artisan, making conscious choices about his materials to match the intention and gravity of the words he was recording. The ink wasn't just a medium, it was part of the message itself, its color subtly influencing how the written word was perceived and received. Of course, all this careful preparation and scientific understanding doesn't guarantee instant success. In fact, the true spirit of ancient craftsmanship is found not in getting it perfect the first time, but in knowing how to fix what goes wrong. Our journey wouldn't be authentic without hitting a few snags, and this is where we connect most deeply with the Roman ink maker. He didn't have a standardized formula from a factory. He had a set of principles and a deep, intuitive understanding of how to correct his course. So, let's roll up our sleeves and play historical detective, troubleshooting our creation as he would have. Imagine our disappointment if, after all that patient grinding and mixing, we dip our reed pen and the ink simply drips from the nib-like black water, spreading uncontrollably into a fuzzy, illegible stain on the papyrus. This is the classic sign of an ink that is too thin. The problem is almost always a lack of body, which means our binder isn't doing its job. The solution lies in two possible adjustments. First, we might not have used enough gum arabic. The remedy is to mix a small additional batch of a very concentrated gum solution, almost a syrup, and then blend it drop by drop into our main ink pot, stirring constantly and testing the consistency after each addition until the ink begins to hold its shape on the pen. The second possibility is that we have the ratio right, but we didn't let the gum fully dissolve, leaving some of its binding power trapped in undissolved crystals. In this case, gentle, sustained heat is the answer. By placing the ink pot in a warm water bath, a Roman might have set it near the embers of a fire. We can encourage the remaining gum to melt fully into the mixture, gradually thickening it to the desired consistency. The opposite problem is just as frustrating. What if the ink is too thick, clinging to the pen in a gloppy mass and refusing to flow onto the page? This turns writing into a chore, with the nib clogging after every other letter. Here, the culprit is an overabundance of either pigment or binder. The most straightforward fix is dilution with a little warm water, but the key is to add the water not all at once, but literally drop by drop, stirring thoroughly after each addition. This patient approach prevents us from overshooting the mark and turning our thick paste back into a watery mess. Sometimes, the issue isn't the overall ratio, but the fineness of the ingredients. If we were impatient during the grinding stage, and our lampblack still contains microscopic clumps, these tiny aggregates can act like miniature dams, blocking the delicate channel in the reed pen. The solution is a return to the mortar and pestle for a more vigorous grinding session, or for a truly refined finish, passing the mixed ink through a fine cloth filter to catch any remaining gritty particles. A Roman might have used a piece of fine linen, straining the ink to achieve that silky, professional quality that separates a master's work from an amateur's attempt. For our iron-gall ink, a unique set of challenges emerges. The most perplexing might be if the ink simply refuses to darken properly, remaining a washed-out gray even after ample time exposed to air. This points to an imbalance in the chemical reaction. The most likely cause is an insufficient amount of tannic acid. Perhaps our oak galls were not fully crushed, or we didn't soak them long enough to extract their full potency. The fix involves creating a new, stronger batch of tannin extract and gradually blending it into the existing pale ink until the chemical balance is restored and the characteristic blue-black finally appears. Another issue specific to iron-gall ink is its potential acidity. If we've been overzealous with the iron sulfate, the ink can become too acidic, which over decades could actually corrode the parchment it's meant to preserve, a phenomenon seen in some historical manuscripts where the writing has eaten through the page. A skilled ink maker would have learned to recognize the astringent bite of an overly acidic batch and known to correct it with a small addition of a mild alkaline substance, like powdered eggshell or chalk, to neutralize the excess acid and ensure the document's long-term survival. This entire process of troubleshooting reveals a profound truth about ancient technology. It wasn't about blindly following a recipe, but about developing a feel for the materials. The Roman craftsman was a practical chemist, constantly observing, adjusting, and problem-solving. His success depended on his ability to diagnose issues through subtle clues. The way the ink dripped from a stick, the sound it made when stirred, the look of a test stroke on a scrap of pottery. Each failed batch was not a defeat, but a lesson that deepened his understanding. By engaging in this same trial and error, we move beyond merely replicating a historical artifact. We begin to understand the intelligence and adaptability required to master a craft in a world without quality control labs or precise measuring instruments. We learn to see with an ancient eye and correct with an ancient hand, completing the circle that connects our modern experiment to the living, breathing reality of the Roman workshop. So far, we've been immersed in the chemistry and craft of ink making, but this remarkable substance didn't exist in a vacuum. It was a product bought and sold, its availability dictated by the same economic forces that shaped Roman life. Stepping back from our workbench, we need to ask a practical question. In a world without corner stores, who could actually afford to write? The answer reveals a fascinating social hierarchy, where the very quality of your words could be determined by the depth of your purse. To understand this, let's translate our ingredients into the language of ancient Roman commerce, using the standard currency of the era, the sestertius. First, consider the humble foundation of our carbon ink, lampblack. For the vast majority of Romans, this was the gateway to literacy. If you had an oil lamp in your home, and most people did, using cheap olive oil, you had a source of pigment. A soldier stationed on Hadrian's Wall, a shopkeeper in Pompeii, or a minor clerk in a provincial town could simply scrape the soot from the inside of their lamp, a resource that was essentially free. The only other cost would be a small amount of low-grade gum, perhaps a locally harvested tree sap rather than fine gum arabic, and some water. For a few sestertii, the equivalent of a cheap meal, an ordinary Roman could assemble a functional, if not professional, ink pot. This accessibility is crucial. It meant that writing wasn't exclusively the domain of the elite. A love letter, a personal diary, a laundry list, or a simple business contract could be penned by someone of very modest means. The written word, in its most basic form, was democratized by the soot of an everyday lamp. However, the moment you sought quality or permanence, the price tag escalated dramatically. Take our key ingredient, gum arabic. This wasn't a local product. It was an import, arriving via long and perilous trade routes from acacia trees in North Africa or the Arabian Peninsula. The cost of transport, taxes, and middlemen would have inflated its price significantly. A small pouch of high-quality gum arabic might cost dozens or even hundreds of sestertii. For context, a common legionary's annual salary was around 300 sestertii. Spending a substantial portion of that on a binder for ink would have been unthinkable. This expense immediately created a tiered system. The professional scribe working for a wealthy patron or a government office would use the best gum arabic to ensure a smooth, reliable flow and a durable bond. His ink was a professional tool, and the cost was a necessary business expense. The average person, however, would likely have made do with a cheaper, stickier substitute like cherry tree gum, or even a diluted honey solution, accepting that their writing might be more prone to smudging or flaking over time. This economic divide becomes even starker when we look at the ingredients for iron-gall ink. While oak galls could be foraged in local woods, the ones considered best for ink were specific types, and gathering them required knowledge and effort. But the real cost driver was the other component, iron sulfate or green vitriol. This chemical required a source, either from specific mines or from an industrial process, and its production was specialized. Acquiring a reliable supply of pure iron sulfate would have been far more expensive than collecting lampblack from a household lamp. Consequently, iron-gall ink was, from its inception, a premium product. It was the ink of choice for the imperial administration, for legal documents that had to withstand challenges, and for the lavish manuscripts commissioned by the very wealthy. When a Roman senator signed an important treaty, the deep, permanent black of the iron-gall ink was a silent statement of authority and resources. Its use signified that the words were not just important, but were backed by the power to make them last. Therefore, the ink pot on a Roman's desk was a subtle indicator of their social and economic standing. A student or a small merchant might use a basic carbon ink, good enough for notes and drafts. A successful lawyer or a mid-level government official would invest in a better quality carbon ink with proper gum arabic for his professional correspondence. But only the state, the ultra-wealthy, or major institutions like temples would routinely use iron-gall ink for their most critical records. This hierarchy of materials echoes throughout history. The cheap ink allowed for the spread of everyday literacy and commerce, the lifeblood of the empire's bureaucracy. The expensive ink preserved the laws and literature that defined Roman civilization for posterity. Our experiment, which started with raw materials, now connects to the living economy of the ancient world, reminding us that the flow of ideas was always channeled through the realities of cost and access. But understanding the theory and the economics of Roman ink only takes us so far. To truly connect with the reality of the scribe's life, we need to turn to the objects they left behind, the silent witnesses to centuries of written thought. The archaeological record provides us with something our recipes cannot: tangible proof. What happens, then, when we shift our gaze from our recreated ink pots to the actual, often beautifully crafted inkwells unearthed from the ashes of Pompeii or the mud of a Roman fort in distant Britain? These finds transform our experiment from a hypothetical reconstruction into a conversation with physical evidence. One of the most evocative collections comes from Pompeii, where the volcanic ash of Mount Vesuvius froze daily life in a single tragic moment. Here, archaeologists have discovered numerous inkwells, most commonly made of bronze or pottery. They are small, portable objects, often designed with a secure, screw-on or push-fit lid. This simple feature is incredibly telling. It wasn't just to prevent spills. It was essential for keeping the ink from evaporating and, more importantly, from becoming contaminated with dust, which would have been a constant nuisance in an open-air workshop or a busy administrative office. Some of the bronze inkwells are works of art in their own right, decorated with intricate engravings or even shaped like miniature amphorae. These were not the tools of a pauper. They speak to a certain status, perhaps belonging to a wealthy merchant, a lawyer, or a government official who valued a fine writing set as a symbol of their profession. Finding these inkwells on desks in Pompeian homes, sometimes next to a stylus and a wax tablet, creates a powerful, intimate snapshot. We can almost picture the owner, interrupted mid-sentence, the lid of his inkwell perhaps left slightly ajar. Moving to the frontiers of the empire, like the Roman forts along Hadrian's Wall in Britain, we find a different kind of inkwell. These are often simpler, sturdier, made of plain pottery or wood. They are the tools of the military bureaucracy, the legionary clerks responsible for recording supplies, payroll, and dispatches. The discovery of inkwells within a barracks or a commandant's headquarters is a potent reminder that the Roman army ran on paperwork as much as it did on discipline and swords. Every soldier's presence, every shipment of grain, every request for reinforcements had to be meticulously written down and archived. A single inkwell found in the cold, wet climate of northern Britain tells a story of immense administrative effort, of maintaining Roman order through the written word in a land far from the empire's heart. The very ordinariness of these frontier inkwells underscores how fundamental writing was to the mechanism of control, reaching every corner of the Roman world. Yet, an empty inkwell can only tell us part of the story. The real breakthrough in recent years has come from the field of residue analysis, where scientists use sophisticated techniques to detect microscopic traces of substances that have been invisible to the naked eye for centuries. Imagine an archaeologist finding a small, unassuming ceramic pot. To most, it might look empty, just stained with dirt. But when a sample from inside that pot is placed under a mass spectrometer, it can reveal the chemical fingerprint of its long evaporated contents. Scientists have done exactly this with pots identified as inkwells. They have detected traces of carbon, consistent with our lamp-black ink. Even more remarkably, they have found evidence of gum, confirming the use of a binder like gum arabic. In some cases, particularly from later Roman periods, the detection of iron and tannin compounds has provided the first physical proof of iron-gall ink use in antiquity, corroborating the literary evidence. Perhaps one of the most fascinating discoveries comes from the analysis of the ink itself on surviving documents. While papyrus rarely survives outside of the exceptionally dry climate of Egypt, we do have a precious few examples. By examining these texts with non-invasive methods like multispectral imaging, researchers can study the chemical composition of the ink without damaging the priceless document. This has allowed them to map the use of different ink types across time and geography. We can now see that a document from 2nd century Egypt used a carbon-based ink, while a later legal text from Ravenna employed iron-gall. This physical evidence helps us build a much more detailed timeline of technological adoption. It shows that the Romans weren't using one single type of ink uniformly across their history, but were experimenting and transitioning, with the more durable iron-gall ink gradually gaining prominence for critical records. Each analyzed residue, each chemically confirmed inkwell, is like a single pixel in a vast picture. Alone, it tells us a small fact, but when combined with hundreds of other finds from across the empire, it allows us to see the full, vibrant image of a civilization that wrote its way to immortality, one carefully measured drop of ink at a time. While we naturally associate ink with the written word, its utility in the Roman world extended far beyond the scrolls of poets and the ledgers of accountants. This versatile substance was a kind of ancient multitool, integrated into the practical, artistic, and even personal spheres of daily life in ways that might surprise us. Imagine walking through the bustling port of Ostia, for instance. Everywhere you look, there are stacks of amphorae, those distinctive clay jars used for transporting everything from Spanish olive oil to Egyptian grain. But how does a dockworker know what's inside or who it belongs to? They didn't rely on memory alone. Using a thick brush and a pot of simple, carbon-based ink, merchants or slaves would paint essential information directly onto the clay surface before firing. These weren't elegant calligraphy. They were quick, functional markings indicating the contents, the owner's name, the weight, and sometimes even the year of production. This was the shipping label of the ancient world, a crucial piece of logistics that allowed the massive Roman supply chain to function. Unlike our paper labels that can peel off or fade, this ink, often mixed with a clay slip, would fuse with the ceramic during firing, becoming a permanent part of the jar itself. Archaeologists today meticulously study these faded marks, which provide a direct window into Roman trade routes, economic patterns, and even individual businesses that operated 2,000 years ago. The use of ink also moved from the permanent to the temporary, serving the needs of a dynamic, fast-paced society. In a world without printed posters or digital displays, how do you advertise a gladiatorial games, announce a public auction, or direct people to a new tavern? You used ink as paint. Temporary signs were often daubed directly onto whitewashed walls in public spaces. A shopkeeper might use a dark ink to quickly update his prices on a board outside his door. Political campaigns during elections were famously waged on the walls of Pompeii, with supporters painting endorsements for their candidates in large, bold letters. This ephemeral use of ink reveals a society that was highly communicative and visually oriented, even in its transient messaging. The ink for these purposes was likely even simpler and cheaper than writing ink, perhaps a mixture of soot and water with a weak binder like vinegar, making it sufficient to last for a few days or weeks before being washed away by rain or painted over by the next announcement. This practice shows us that Roman ink wasn't always about creating a permanent record. Sometimes, it was about seizing the moment and communicating with the crowd right now. Perhaps the most intriguing alternative use ventures into the realm of personal adornment. There is compelling evidence that Romans, particularly women, used forms of ink in their cosmetics. While kohl, made from powdered stibnite or galena, was the most common eyeliner, a substance very similar to ink could have been used to darken eyebrows or even as a form of hair dye. A concentrated, paste-like mixture of soot and a gum binder would have been ideal for this purpose, providing a rich, matte black that could define the features. Furthermore, the artistic applications extended beyond the page. While grand Roman murals were executed in vibrant mineral pigments, ink would have been the go-to medium for preliminary sketches. An artist planning a vast wall painting in a villa might first lay out the entire composition in diluted ink, creating a monochrome underdrawing to guide the application of expensive colors like cinnabar red or Egyptian blue. This practice, known as synopia, ensured the proportions and perspective were correct before committing to the final, costly pigments. In this role, ink was the unseen foundation of great art, the structural skeleton upon which the colorful skin of the masterpiece was built. From labeling cargo to sketching frescoes, this simple technology proved to be as adaptable as the Romans themselves, seamlessly weaving itself into the very fabric of their commercial, social, and creative lives. Considering the environmental footprint of our project leads to a surprising realization about the inherent sustainability of ancient Roman technology. When we look at the ingredients we've gathered, lampblack from a burning oil, gum arabic from tree sap, oak galls from a natural tree growth, and simple iron salts, we are looking at a supply chain that is almost entirely biodegradable and derived from renewable, or at least minimally processed, natural resources. There is no plastic, no synthetic petrochemical dye, no industrial solvent. At the end of its life, a pot of Roman carbon ink, if spilled on the ground, would simply break down into carbon, water, and natural gums, returning to the earth without leaving a toxic legacy. This stands in stark contrast to the complex chemistry of many modern permanent inks, which often rely on volatile organic compounds and heavy metals that can pose significant challenges for disposal and environmental health. This ecological advantage, however, comes with important context and should not be viewed through an overly romantic lens. The sustainability of Roman ink production was largely unintentional, a byproduct of technological limitation rather than a conscious ethical choice. They used these materials because they were the only ones available. Furthermore, we must consider the scale of production. While an individual scribe making ink for his own use had a negligible environmental impact, we have to ask what the cumulative effect was for an empire that wrote on an industrial scale. The demand for high-quality lampblack, for instance, would have required the dedicated burning of oils or resins. While this was on a far smaller scale than modern industrial pollution, it still represented a localized consumption of resources. The harvesting of gum arabic involved long-distance trade networks, with all the environmental costs of ancient shipping, the consumption of wood for shipbuilding, the forage for animals carrying goods over land. Yet, when we place these ancient practices side by side with modern industrial ink manufacturing, the difference in philosophy is profound. Our Roman recipe is a model of a circular economy, albeit a primitive one. The lampblack is essentially a form of waste product, the soot from a lamp used for light being repurposed into a valuable commodity. The oak galls are a byproduct of a natural process on a tree that continues to live and grow. There is a beautiful efficiency in this, a way of seeing potential value in materials that might otherwise be discarded. This stands against our modern linear model of take, make, dispose, where virgin materials are extracted, intensively processed in factories requiring massive energy inputs, and often end up as waste in a landfill. The Roman approach was deeply integrated with the natural world's cycles, not separate from them. This comparison offers a powerful lesson for our own time. We are now seeking ways to develop greener technologies and reduce our environmental impact, often by looking to biomimicry and natural processes. The Roman ink recipe is a historical case study in exactly that principle. It demonstrates that high-performance, durable products can be created from simple, naturally occurring substances. The challenge for modern innovators is to harness this ancient wisdom, but scale it with contemporary scientific understanding, creating new materials that have the low environmental footprint of Roman ink, but can be produced ethically and efficiently for a global population. Perhaps the future of sustainable design doesn't always lie in inventing something completely new, but in rediscovering the elegant, time-tested solutions of the past and re-engineering them for a modern world. Our small pot of ink, therefore, becomes more than a historical curiosity. It transforms into a touchstone for a conversation about how we can live more harmoniously with our environment, learning from the resourcefulness of those who came before us. After all the grinding, mixing, and testing, the moment has arrived to step fully into the role we've been preparing for. We are no longer just experimenters. For this next part of our journey, we become scribes. The tools of the trade are laid out before us. Our most successful batch of iron-gall ink, possessing that deep, cool blue-black hue we now know signifies permanence. A freshly cut and carefully split reed pen, its nib honed to a fine point, and a small, creamy piece of parchment, stretched and prepared according to traditional methods. This is our scriptorium, our place of work, and our task is to bridge 200 years with a simple, deliberate act of writing. We have chosen a line from Virgil's Aeneid, a text that would have been familiar to any educated Roman, forsan et hic olim meminus iuvabit. Perhaps one day we will look back on even these troubles with joy. The sentiment feels uniquely fitting for our own endeavor, a project that has had its own share of challenges and discoveries. The preparation is a ritual in itself. We take our seat, arranging the parchment on a slanted writing surface to mimic the angle of a Roman writing desk. We place the ink pot securely to our right, within easy reach but not so close as to risk a catastrophic spill. The first physical step is to dip the reed pen. There is a certain tension in this simple action. You submerge the split nib fully, allowing a moment for the capillary action to draw the ink up into the shaft. As you lift it, you watch for that perfect single droplet to form at the tip, and not dripping but waiting. Then you bring the pen to the parchment. The moment of contact is decisive. You cannot hesitate. The reed touches the surface with a faint, satisfying scratch, a sound that is the audible signature of this ancient technology. The act of forming the letters is a lesson in physical discipline that no modern pen can teach. Your entire arm is engaged, not just your fingers, to create the strong vertical downstroke of a letter like F or H. You pull the pen toward your body with a gentle, consistent pressure. You can feel the fibrous surface of the parchment gripping the nib, offering a slight resistance that gives you remarkable control. For the thin, horizontal strokes, you push the pen sideways, a motion that inherently releases less ink, creating that beautiful contrast between thick and thin lines that defines Roman calligraphy. The famous serifs, those small finishing strokes at the end of each main line, are not decorative add-ons but the natural consequence of the pen's movement. A slight pause and lift at the beginning and a tiny flick at the end to prevent a blob of ink. What looks like a sophisticated artistic style is, in reality, the most efficient way to use this specific tool. It is ergonomics transformed into elegance. Writing a full sentence reveals the rhythm of the work. There is a natural pause after every few words as you must re-ink the pen. This forced interruption creates a measured, thoughtful pace. You cannot rush. Each dip is a chance to glance at what you've written, to check the consistency of the ink flow, and to prepare mentally for the next phrase. This rhythmic work, right dip, is a world away from the uninterrupted stream of a ballpoint. It makes you appreciate the immense concentration and muscle memory required of a professional scribe who might spend 10 hours a day copying an entire scroll. His hand would have moved with an economy of motion we can only aspire to, each letter perfectly formed through thousands of hours of practice. Our own writing is slower, more deliberate, each character a conscious effort to replicate a historical form. As the ink begins to dry on the page, we witness the final, magical stage of the iron-gall process firsthand. The words, initially a pale gray, slowly deepen before our eyes. Over the course of a minute, they shift through shades of purple and blue before settling into that definitive, profound black. Watching this transformation is like watching the words themselves take a deep breath and settle into the parchment, becoming a permanent part of its substance. It is a deeply satisfying conclusion to our entire experiment. We are not just looking at a phrase we wrote. We are looking at a physical object that has been chemically altered, a piece of the past made tangible in the present. The line from Virgil now exists on our parchment with the same authority as it does in a 2,000-year-old manuscript. This successful recreation is the ultimate validation of our methods. It proves that the knowledge passed down by Pliny and others was not merely theoretical, but was a practical, effective technology that worked precisely as described. By completing this act, we haven't just learned about history, we have, in a very small but significant way, participated in it. This remarkable journey into the past, from gathering raw materials to watching ink oxidize on parchment, might seem like a closed chapter, a fascinating but ultimately obsolete craft. Yet, the principles we've uncovered are experiencing a vibrant renaissance in the most unexpected of places: the studios of contemporary artists, calligraphers, and even forward-thinking chemists. The ancient Roman approach to ink making offers more than just a history lesson. It provides a powerful toolkit of ideas that feel remarkably urgent in our modern world. For today's calligraphers, the appeal is deeply aesthetic and tactile. While they have access to a vast array of consistent, commercially produced inks, many are drawn to the unique, organic character of handmade iron-gall and carbon inks. A calligraphy artist might explain that no two handmade batches are ever exactly identical. The slight variations in color, the subtle warmth of a carbon ink versus the cool severity of an iron-gall, and the way the ink interacts with different papers create a living dialogue between the medium and the artist. This unpredictability is not a flaw but a feature, introducing an element of the handcrafted into every stroke that mass-produced inks simply cannot replicate. The process of making the ink itself becomes a form of meditation, a way to connect intimately with the entire creative act, from the sourcing of materials to the final flourish of the pen. It transforms writing from a mere act of transcription into a holistic art form. This resurgence is also driven by a growing desire for archival quality and permanence in an increasingly digital and ephemeral age. Artists creating works meant to last for generations look to the proven track record of these ancient recipes. They know that a painting or drawing executed with a well-made iron-gall ink has a fighting chance of surviving for centuries, its lines chemically bonded to the paper. This is a stark contrast to some modern art supplies, whose long-term stability is still unknown. Furthermore, the movement towards natural pigments and sustainable art practices finds a perfect ally in historical ink making. The core ingredients, soot, oak galls, gum arabic, are biodegradable and sourced from renewable or waste materials. In an era concerned with microplastics and toxic waste, the environmental profile of Roman ink is incredibly appealing. Modern artisans are taking this a step further, experimenting with locally foraged materials. Instead of imported gum arabic, an artist might use sap from a cherry tree in their own backyard. Instead of lampblack from a specific oil, they might collect soot from a responsibly managed wood-burning stove. This practice, known as place-based making, grounds the artwork not just in historical technique, but in the very ecology of the artist's immediate environment, creating a profound connection between the art, the artist, and the land. Perhaps the most profound lesson for our contemporary world lies in the philosophy embedded within the Roman method, one of deep material understanding and resourcefulness. The Roman ink maker wasn't a passive consumer, he was an active participant in the creation of his tools. He understood the properties of his materials on a visceral level: the grind of the soot, the dissolve of the gum, the reaction of the iron. This stands in direct opposition to our modern reality, where we are often separated from the origins and composition of the products we use. We click a button and a bottle of ink arrives at our door, its contents a proprietary mystery. By relearning these ancient processes, we reclaim a sense of agency and knowledge. We become less like users and more like collaborators with our materials. This has powerful implications for education, encouraging a hands-on, interdisciplinary approach that blends history, chemistry, and art. It teaches problem-solving, patience, and respect for the raw elements of our world. The journey of creating Roman ink demonstrates that some of the most elegant and enduring solutions are not necessarily the most technologically complex, but rather those that work in harmony with natural principles. In looking back 20 years, we might just be finding a path forward to a more thoughtful, sustainable, and deeply connected way of creating. Our successful recreation of Roman ink is a satisfying conclusion in itself, but it also opens a fascinating window into a much longer story. The techniques we've painstakingly replicated were not a dead end. They were the vital foundation upon which 1,000 years of European writing would be built. To truly appreciate the Roman achievement, we need to fast forward through time and place our humble ink pot next to the dazzling illuminated manuscripts of the medieval and Renaissance periods. The journey from a Roman scribe's workbench to the scriptorium of a Gothic monastery is one of remarkable continuity and thoughtful refinement. The core technology, the brilliant chemical reaction of iron-gall ink, remained essentially the same. What changed was not the fundamental recipe, but the meticulousness of its execution and the specific demands of new artistic and cultural ambitions. The most significant evolution lies in the quest for consistency and purity. Our Roman experiment involved a degree of educated guesswork, interpreting vague descriptions like a portion of gum or well-ground galls. A medieval monk, whose entire life might be dedicated to copying sacred texts, had the time and the devotional incentive to perfect this process. He would have been far more fastidious about his ingredients. He might have selected only the largest, densest oak galls, knowing they contain the highest concentration of tannic acid. He would have purified his iron sulfate by repeatedly dissolving and crystallizing it to remove impurities that could lead to premature corrosion of the precious vellum. The goal was no longer just a serviceable ink, but an ink of such perfection that it would honor the divine words it was used to inscribe. This drive for purity resulted in an ink that was often more stable and less acidic than its Roman predecessor, a crucial factor in the survival of so many medieval manuscripts in such brilliant condition centuries later. This refinement directly served a new artistic purpose, the rise of illumination. While Roman documents were largely utilitarian, focused on clarity and administrative efficiency, medieval manuscripts were often magnificent works of art. The ink itself had to play a dual role. It needed to be flawless for the crisp, black text of the main body, but it also had to coexist harmoniously with vibrant mineral pigments like ultramarine blue, vermilion red, and gold leaf. A poorly made, acidic ink could eventually bleed into or degrade these adjacent colors. Therefore, the ink recipe was adjusted not just for writing, but for its role in a larger aesthetic ensemble. Furthermore, the art of calligraphy itself evolved, demanding new qualities from the ink. The intricate, sharp serifs and hair-thin lines of Gothic script required an ink with an even finer particle suspension and a more predictable flow than the broader, more robust Roman capitals. The medieval ink maker was, in effect, collaborating with the illuminator and the calligrapher, fine-tuning his product to meet the highest standards of visual splendor. By the time of the Renaissance, this perfected iron-gall ink was the undisputed medium of masters like Leonardo da Vinci and Michelangelo for their drawings. Look closely at Leonardo's sketches, and you see the same characteristics we observed in our own experiment: the cool blue-black tone, the incredible durability, and the ability to create a wide range of tones from a faint wash to a deep, intense black. The ink had transcended its administrative origins to become a primary tool of artistic genius. The fundamental chemistry that our Roman craftsmen had harnessed for record-keeping was now being used to explore human anatomy, conceptualize flying machines, and capture the sublime beauty of the natural world. This continuity is nothing short of astounding. The ink used to draft a Roman tax record in the 2nd century and the ink used to sketch the Mona Lisa in the 16th century were close cousins, separated more by the skill of the maker than by the underlying principle. Seeing this direct lineage helps us reframe our entire experiment. We weren't just recreating a historical artifact. We were tracing the origin point of a technology that enabled the preservation of Western knowledge and art for over a millennium. The Roman invention of reliable iron-gall ink was a quiet revolution. It provided the durable medium that carried Latin literature through the Dark Ages, that recorded the intellectual reawakening of the Middle Ages, and that facilitated the explosive creativity of the Renaissance. Every time we admire the precise black lettering in a medieval Bible or the fluid lines of a Renaissance drawing, we are seeing the indirect legacy of Roman ingenuity. Our small pot of ink, then, connects us not only to a scribe in ancient Rome, but to an unbroken chain of monks, scholars, and artists who used this same remarkable substance to build, preserve, and illuminate the world of ideas. And so, our experiment comes to a close, not with a final period, but with a profound sense of connection. We began with simple elements: soot, gum, water, and a spark of curiosity. And through the meticulous recreation of ancient methods, we've arrived at something truly remarkable: a living, flowing ink. This journey has demonstrated that Roman technology was far more than just practical. It was a sophisticated interplay of chemistry, material science, and refined craft. Their ink wasn't a haphazard mixture, but a carefully calibrated substance, born from centuries of observation and experimentation. We've witnessed firsthand how the choice between a warm, immediate carbon black and a cool, chemically transformative iron-gall was a deliberate decision, reflecting the intended purpose and permanence of the written word. This hands-on process has transformed our understanding from an abstract historical fact into a tangible, physical truth. The true power of this exercise, however, lies in the connection it forges. Holding a reed pen dipped in ink we made ourselves and watching it glide across parchment is an experience that transcends books and documentaries. It's a moment of direct, unmediated contact with the past. We are performing the same actions, solving the same problems, and feeling the same satisfaction as a Roman scribe 2,000 years ago. The faint scratch of the nib, the slow darkening of the iron-gall line, the smell of the gum arabic, these sensory details are a form of time travel. They make the ancient world feel immediate and real, not as a collection of ruins in a museum, but as a living culture of ingenious, resourceful people. The ink in our pot is more than a replica. It is a physical thread tying our present curiosity to their everyday reality, a testament to an ingenuity so effective that their very words have defied time itself. This legacy of Roman ink is, quite literally, the foundation of Western history. The recipes we followed in our workshop were not a dead end. They were the essential technology that monks in cold scriptoria would perfect to copy the Bible, that scholars in Baghdad would use to translate Greek philosophy, and that Renaissance masters like Leonardo da Vinci would employ to sketch their visionary inventions. The durable bond of iron-gall ink ensured that laws, literature, and personal thoughts could survive fires, floods, and the slow erosion of centuries. Every time we read a translation of a Roman letter or admire a medieval manuscript, we are benefiting from the success of this ancient craft. Our small experiment thus becomes a window into a much larger story, the story of how human knowledge was preserved and transmitted, all starting with a simple, dark liquid crafted with care and profound understanding. This journey leaves us with a compelling question. What other lost arts are waiting to be rediscovered through the power of hands-on experimentation? The field of experimental archaeology offers endless possibilities. Perhaps we could explore the secrets of Roman concrete, mixing volcanic ash and lime to understand why their structures still stand while modern counterparts crumble. We might attempt to forge a blade using the exact methods of a Germanic blacksmith from the Iron Age, feeling the differences in steel quality and tempering techniques. Or we could turn our attention to ancient textiles, from the cultivation of flax to the intricate process of weaving on a period-accurate loom. Each of these projects offers the same unique reward, a deep, empathetic understanding of the past that no textbook can provide. We learn not just what people did, but how they thought, how they solved problems, and how they interacted with the material world around them. Your curiosity is the most important ingredient in this ongoing exploration. The history of technology is a vast and largely untapped resource for incredible stories of innovation. What forgotten process or ancient invention fascinates you the most? Is there a particular mystery from the past that you would love to see us tackle in a future project? Share your ideas and suggestions in the comments below. Your input will directly shape our next adventure into the past, as we continue to use hands-on discovery to bridge the gap between then and now, one fascinating experiment at a time.